Yury?
Yeah, let me try one more attempt. Okay. I still can't see the appropriate window. Do you see my screen?
Oh, don't.
No. Okay. Okay. So if possible, please download my PDF file. Okay, fine.
Yeah, good.
Now, how I will jump to next slide.
Just ask me.
Okay, thank you very much. So I will be talking about Kadamtsev-Peculiarity equation, which is commonly used model equation for the description of nonlinear waves in dispersive media. And this equation, so please next slide, was derived in 1970. And later it was discovered that actually there are two versions of this equation. One of them is positive parameter beta, which is currently called KP2 equation, which is strongly integrable equation, possessing exact solution and the complete integrability. And there is another version, KP1, when dispersive parameter beta is negative. And this equation, according to the Harvard terminology, is weakly integrable. This equation never ceases to amaze us with its remarkable exact solutions. And last time in the previous meeting, I presented some interesting solution describing interaction of two-dimensional solitons. But in recent years, there were obtained a lot more exact solutions, which I will try to present today. But first of all, I will briefly remind you which phenomena this equation can describe. On the next slide, you can see, next slide, please. On the next slide, okay. So both these equations possess a single soliton solution, which describes solitary wave propagating at an angle to the x-axis. But in the case of KP2 equation, this solution is stable with respect to small perturbations, whereas in the case of KP1 equation, such a solution is unstable with respect to modulation. On the next slide, you can see the physical explanation of such focusing and defocusing phenomena within the framework of Kadamtsev-Peculiarity equation, which depends on the sign of dispersive parameter beta. On the next slide, you can see the situation when the KP2 equation is applicable. This is a satellite image of internal waves, internal solitons. And here you can see that solitary waves can propagate in the autumn as quasi-plane waves, slightly modulated in the perpendicular direction y. And this is exactly the situation which can be described by Kadamtsev-Peculiarity equation. In the next slide, you can see solitary waves interacting on the surface of a shallow water. In the left corner, in blue frame, you can see the theoretical prediction. This is an exact solution of Kadamtsev-Peculiarity equation for two plane soliton interacting under the angle. And above this frame, you can see the photo of two solitary waves interacting in a very similar way. In the right-hand side, you can see some other types of soliton interaction. On the next slide, you can see that original Kadamtsev-Peculiarity equation can be presented in so-called Hirota variables. If we make such a simple transformation, we can transfer the original equation to this bilinear form. This equation presented in Hirota variables, and at the first glance, it looks even more complicated than the original one. But nevertheless, this equation possesses simple solutions. In particular, in both cases, for beta positive or negative, there is a solution which can be presented as a combination of 1 plus exponential function of omega t minus kxx minus kyy. So in original variables, this solution describes a solitary wave propagating under an angle to axis x and y. On the next slide, you can see that in the case of negative beta in the media with negative parameter beta, Hirota equation possesses another very simple solution, which is represented here by quadratic polynomial. In the original variables here, you can see that this solution can be presented in terms of rational function, and this solution describes localized in all directions, localized solution which decays algebraically when x tends to infinity. It decays as x to minus 2 and y to minus 2 if we go to infinity in y direction. On the next slide, you can see the structure of such two-dimensional solitary waves, which are called lumps. They are symmetric lumps propagating along axis x, and skew lumps which propagate under the angle to the x-axis, and such skew lumps are non-symmetrical with respect to x and y directions. Next slide, please. Here you can see the development of focusing instability when we have initially a plane wave in the left frame slightly modulated along the front. In the process of development of such instability, we can see that a chain of lumps emerge from initial solitary wave, and when x goes to infinity, we have just a pure lump chain and pure plane solitary wave. Nevertheless, each of these entities are also unstable. In the next slide, you can see that even a periodic chain of lumps under small modulation becomes unstable, and we can see that it splits again into two different chains. One of them of higher amplitude separates from the another periodic chain of lumps of a smaller amplitude. But individual lump is quite a stable entity. Next slide, please. Later, in my papers with my co-authors, it was found, first of all, numerically the existence of stationary bilump, and then such a solution was derived analytically in my paper with Dmitry Pelinovsky, and moreover, it was shown that it can be triple stationary propagating triple lump, and even more complicated structure contains of several lumps. In the next slide, you can see an example of triple lumps. This one where two lumps propagate along axis x and another one on the side. And also there is a solution which represents two lumps propagating side by side and another one propagating in front of them. I'd like to emphasize that all these structures are stationary structures, but all of them are unstable with respect to small perturbations, and in the result they disintegrate into the number of individual lumps. Next slide, please. Recently, it was found a very efficient method which allows us to construct some more interesting exact analytical solutions. This approach is based on so-called Gramian matrices. Within the framework of this method, we can present a solution again in terms of Hirota transform, where function tau can be presented as a determinant of such a matrix. In this matrix, there are functions psi j. These functions psi j are solutions of a linear set of equations shown here. It was shown for the first time in the seminal paper by Zakharov and Shabbat in 1974. And what is amazing, that actually solutions of these nonlinear equations can be obtained through the solution of this linear set of equations. And in particular, we can find a lot of linearly independent solutions of this set of equations just by separation of variables. In the next slide, we can see that the simplest solutions can be presented in a following way. If we choose properly this matrix C, J, K, and this polynomial P. The polynomial P is just a derivative with respect to spectral parameter lambda as order derivative times such an exponential function. So this is so-called quasi-polynomial. The simplest solution can be obtained when we choose only one function psi. M tells us how many linearly independent solutions we use. If we use only one, and if we choose such simple set of parameters, then we obtain a plane solitary wave, this one. On the next slide, you will see how easily can be obtained through this approach a solution for the lump. So these solutions were very well known, but within the framework of this method, we show how easily they can be obtained. Non-trivial solutions can be obtained if we choose, show please the next slide, if we choose some other parameters for the Gramian matrix, which are shown here. And the first one describes the interaction of lump and line or plane solitary wave. So here you can see that matrix is of a rank 1, and there is another process when in first case a soliton is observing by plane solitary wave. In the second case, it is emitting by solitary wave. Next slide illustrates the process. So at the initial instant of time, we have such a line solitary wave, and then in the process of propagation, it emits a lump, and after a while, it again becomes just a plain solitary wave with lump propagating to the right-hand side. And of course, inverse process is also possible when a lump is observed by plain solitary wave, and then at the infinity, we have just a plain solitary wave. In the next slide, you can see that within the framework of this approach, by choosing different simple parameters, we can observe the interaction of lump and plane solitary wave. So here you can see that they are separated, well separated. Then in the process of interaction, we have such symmetric construction, which splits again, and at plus infinity, we see that again, there is a plane solitary wave and a lump. In the next slide, we present a particular case when lump can be absorbed by plane solitary wave, and as a result, we obtain such stationary propagating construction, which represents a lump sitting on a plane solitary wave. One more interesting examples are shown on the next slides. So in this slide, if we choose two linearly independent psi functions and such simple set of parameters, then we can describe two weakly bound line solitons which exchange by a lump. In the next slide, you will see such a process. So at the initial instant of time, we have two plane solitary waves of almost equal amplitudes propagating along axis x. At certain instant of time, one of plane solitons emits a lump which exist in space and in time only in a finite interval. After that, this lump is absorbed by another solitary wave, and at plus infinity, we again have two plane solitary waves which move with respect to each other very slowly, so that the distance between them increases logarithmically with time. And so what is remarkable, that this lump exists only within finite interval. So it appears from nothing, and then it disappears again. To a certain extent, it can be considered as a rogue wave, which exists only in finite time interval. Next slide shows that at certain parameters, this messenger, this lump messenger, can be invisible. So its amplitude is so small that at some instant of time, one soliton plane soliton approach another one, but you can't see a lump between them. After them, they separate again, and at plus infinity, we still can observe, we can see only two plane solitons slowly moving with respect to each other. In the next slide, you can see even more complicated solutions when a chain of lumps approaches a plane soliton, and they are absorbed by plane soliton, so that at plus infinity we have only one plane soliton, and there are no lumps. Of course, this process is reversible because this Kadamtsev-Peculiarity equation is without losses, and so we can observe the inverse process when a plane solitary wave can emit a chain of lumps. Next slide, please. In this slide, you can see that two plane solitons can exchange by a chain of lumps. So at certain instant of time, one plane soliton emit a chain of lumps, which is absorbed by another plane soliton, so that at plus infinity we again have two solitons without lumps between them, so that this chain of lumps exists only within finite time interval. Similar solutions recently were obtained by different authors, and they are published in these papers. And if I have time, I can show you some elementary acts of lump interaction. Unfortunately, I can't show the movie. So on the next slide, you can see this one and all other slides. You can see the interaction of lumps between each other. But all these type of interactions I have presented in the previous KOZWave meeting. So practically that's it what I was going to tell you, and I am ready to answer to your questions.
Thank you for that. Have we any questions from the audience?
On the next slide, you can see recent publications.
Thank you. There seems a remarkable diversity of analytic solutions available by the method you showed us.
Yeah. As I mentioned already, this equation never ceases to amaze us with such remarkable solutions.
Are there any applications that you can see for these type of processes?
As I mentioned in the beginning, for the KP2 equations, there are several observations of plane solitary waves for internal waves or for surface waves in the ocean. But for lumps, I don't know any real observation